All right, I'm going to look at homework 6. I've got a variety of frequency response, transfer functions for which I'd like to get the magnitude and phase relationships. So let's do that. Problem 1, G of S is equal to 15 over S plus 30. All right. So what I'm asking is, this is for homework / quiz. You're supposed to obtain the expressions for the magnitude and the phase portions of that transfer function, and then evaluate the magnitude and phase at a frequency of 10 radians per second. So to that end, let's do that. What we know is that the magnitude of this is going to be magnitude of G of J omega. Okay, that's the expression for the magnitude of the transfer function. So in this case, that will be the magnitude of 15 divided by the magnitude of J omega plus 30. We replace and the magnitude of the entire expression is equal to the ratio of the magnitude of the numerator divided by the magnitude of the denominator. And so the magnitude of 15, I'll bet you can figure that one out, that is 15. Nice. The magnitude of J omega plus 30 is going to be the real part squared plus the imaginary part squared and the square root of that. It is not going to be, let's just do it this way, it's 30 squared, okay, that's the real part squared, and there's always a temptation for some students to take this entire expression, J omega, and square it. That's not what you're doing. The imaginary part is the omega, so it's the square root of 30 squared plus omega squared, like that. The J does get squared later in second order systems, for example, but not in this context. And so that's it. That is the expression for the magnitude G of J omega. The phase angle of G of J omega is going to be the phase angle of the numerator. So that's the angle of 15, the real number 15, minus the angle of the denominator, J omega plus 30, like that. So the phase angle for 15, we simply have a point out on the real axis at location 15. The angle of that is 0. Okay, so this is equal to 0 degrees. That's the first term. Minus the angle of J omega plus 30. So we say, okay, omega is going to be a positive number. We're not going to be driving this with negative frequencies. So we have, if this is again our complex plane, the real part maybe is right here, maybe that's 30. And then as omega grows, omega gets to go from 0 all the way up, then it's going to go up like this. And so we have these angles like that. What we see is that this is the imaginary part, omega, and this is the real part, 30. And the angle then is the inverse tangent of the imaginary part over the real part. So it's minus inverse tangent in this case of the imaginary part, which is omega, divided by the real part, which is 30. Okay, that's our expression. So let me get rid of this stuff. All right. So in other words, maybe it's time for a new marker. What we have on this then is that the angle G of J omega is simply equal to negative inverse tangent of omega over 30. So, where are we at? The other questions, this is basically part A was get the expressions, which would be this expression and this expression. And part B is evaluate those expressions at a frequency of 10 radians per second. And so the magnitude G of J10 is going to be then 15 over the square root of 30 squared plus 10 squared, square root of that, not equal to 15, well, anyways, you can do your fractions and square roots and all that yourself. 15 over, what's that, 30 squared is going to be 900 plus 100, so square root of 1,000, which is equal to 15 over 10 square root of 10, right? Whatever that is. It's 1.5 over the square root of 10. Shucks if I know, 1.5. The square root of 10 is about, what, 3 point something? 3 times 3.333, so it's going to be somewhere between 3 and 3.333. So 15 divided by 1.5 divided by 3, about 0.5, a little under 0.5. Okay, less than 0.5. And what did I say the answer was here? 0.4743. Whoop-de-dee. Okay, so yeah, that's the answer. I'm not going to bother getting on my phone to do the calculations. 0.4743. You do the numbers yourself. The expression is correct. The phase angle is actually going to be then angle G of J10 is equal to minus the inverse tangent of 10 over 30. So we're looking at 10 up, that's not it. 1, 2, 3, 1, I don't know, what is that, about 20 degrees or so, something in that vicinity, but that's a positive angle. That is what I'm evaluating here. There's the tangent of 10 over 30, and then I got to do the negative of that because that's the way that it goes. And so this is actually equal to, once again, wow, I blew that one. Oh no, I didn't, negative 18.44. All right, you can use radians if you want. I don't know, I tend to think in terms of degrees and then do math in terms of radians. So that's problem one. Pretty straightforward how to do that one. Problem two, may as well move over and leave that one intact for now, and we'll erase everything all at once. G of S is equal to 30 over S plus 15. Sure would be nice to have more light in this room, wouldn't there be? I wonder if I can do that. Hey, magic light, well, you know. 30 over S plus 15. So just cutting to the chase, magnitude G of J omega is going to be 30 over the magnitude of J omega plus 15 is equal to 30 over the square root of 15 squared plus omega squared is equal to 30 over square root of 15 squared is what, 225? No, that's not right. 625, isn't it? Yeah, it is 225. Yeah. 10 times 15 is 150 plus another 75 makes 225. I'm thinking 25 squared is 625 plus omega squared. The angle G of J omega is going to be equal to 0 degrees because that's the angle of the numerator, which is the angle of 30 degrees, not the angle of the real number 30, which is 0 degrees, minus the angle of the denominator. So that's going to be minus the angle of J omega plus 15 is equal to minus the inverse tangent of omega, the imaginary part, over 15. All right, so once again, just for the fun of it, if this is going to be the imaginary part, it's going to be 10. So 1, 2, 3, 1, 2. That's the angle that we're looking for. Partially the angle. That's the inverse tangent of omega over 15. Then we have to do the negative of it. And so the angle G of J10 is equal to, what did I say? I think it's in here. Negative 33.69 degrees. Work that out yourself. Okay? And also the angle, the magnitude G of J10 is going to be equal to 30 over the square root of what? 225 plus 100 over 325, which, shucks if I know what that's going to end up being in my hand anyways. Let's not bother with that. Let's see. The answer is 1.664. Alright. I'm cheating on that. Yes, getting the answers that way. What I'm trying to show you is the process, and then you can do the calculations yourselves. Okay, that's problems 1. Problem 2. Problem 3 gets to be, of course, we'll notch it up a little bit in terms of difficulty. Every one of these problems I'm trying to illustrate something with. Some just to show you the motions, which is really what the first order ones are about. Second order ones trying to show that you got to be careful with the phase angles on how you do that. A lot of people have trouble in, say, 360 when the phase, they think it gets on the other side of 180 degrees or on the other side of positive 90. Yeah, let's see what happens here. So, problem number 3, S is equal to, what do I have? 104 over S squared plus 20S plus 104. Well, you know, at low frequencies, the magnitude is 1. It's this coefficient over that coefficient. That would be the response to a step input, as it turns out. But yeah, I'll say that for another day. Now what am I asking for? Magnitude G of J omega is equal to the magnitude of the numerator, which is 104, divided by the magnitude of the denominator. Well, first I have to construct G of J omega is equal to 104 over, all right, J omega squared. You do leave the J in there when you have it as G of J omega. You have plus 20 J omega, that's for the S right there, plus 104. So if G of S is equal to this, then we say G of J omega is equal to this, is equal to 104 over, let's do the real parts first, 104. This J omega squared means it's minus omega squared. That is the real part, plus J times 20 omega. 20 omega is the imaginary part. All right? So let's write that in down here then, or to utilize that, the magnitude then of the denominator is the real part squared, 104 minus omega squared, plus the imaginary part, not the J. Here you use the J, when we get the magnitude, we're taking the imaginary part. Can't emphasize that enough, trying to avoid this problem on the test, plus 20 omega squared. So if you had left the J in here, you'd have a negative. That would be wrong. And then, of course, we have to do the square root of those two expressions as well. So the magnitude G of J10 is going to be equal to 104 over 104 minus omega squared is going to be 104 minus 100, which is going to be 4. Okay, we're going to square that, so that'll be 16 plus 20 times 10 is 200 squared. 200 squared is going to be what, 40,000? Yeah, something like that. Square root of all that fun stuff is equal to, hope we got that right, 0.5199. Yeah, that sounds about right. Why do I say that it sounds about right? Is 16 small relative to 40,000? I would have to say yes, it is. So really, the square root of 16 plus 40,000 is pretty much the square root of 40,000, which is 200, is what we were saying. So 104 over 200 sounds a lot like 0.5199. There's a little bit of slop in there with the 16, but pretty darn close. What is it? 104 over 200 is going to be 4 over 200, 0.02. Oh, I hope I got those numbers. Maybe I'm yeah, I'm pretty confident we got that all right. So we got the magnitude of G of J omega. We got the expression magnitude of G of J10. Let's do the phase now. Angle of G of J omega is equal to the angle of this expression, which is the angle of the numerator. It's a real number, therefore the angle is 0 degrees, minus the angle of the denominator, which is the inverse tangent of, and this is actually the inverse tangent too. This is the inverse tangent of the imaginary of the numerator divided by the real of the numerator. I mean, we can actually do that. All right, maybe that's a good idea. It's inverse tangent of the imaginary of the numerator is 0, the real of the numerator is 104, minus inverse tangent of the imaginary of the denominator, which is 20 omega, do not put in the J, over 104 minus omega squared. This expression is 0. 0 over 104 is 0, by the way, but it's not just that. It's the fact that the imaginary part, there's a real part here, and the imaginary part is 0. Therefore, I really would suggest you leave it in terms of a numerator and denominator. Don't try to evaluate this expression, except on your calculator. Now, we'll take it, think about it. How about I do that until you think about it, okay? So this is actually equal to, 0 degrees, so let's get rid of that, minus the inverse tangent of 20 omega over 104 minus omega squared. And so the angle g of j10 is going to be equal to minus the inverse tangent of 200 divided by 104 minus omega squared is going to be 4. All right? Now let's take a look at what that turns out to be as far as in the phase plane, or not the phase plane, but the complex plane. The imaginary part is 200, the real part is 4, so the real part is here, the imaginary part is somewhere up there. So we're going to have something pretty darn close to 90 degrees when we do the inverse tangent of 200 over 4, and we do the negative of that inverse tangent, about equal to negative 90 degrees. The real answer is going to be, pardon the pun, the real answer, it's actually equal to 88.86 degrees negative. All right? Okay. I hope that clears up a few things on that one. Let's see. Number 4. I'm going to take a departure from this for a second and actually suggest that, because I think I was a little remiss in this assignment, I gave you the phase angles they're all less than, in magnitude, than 90 degrees. It really would be important or illustrative, I think, for us to take a look and figure out what the angle is going to be for, say, 20 radians per second as a frequency. This J10 means that we're actually driving the system at a frequency of 10 radians per second. So, for the fun of it, just because, magnitude G of J20 is going to be equal to, so we're driving the system at 20 radians per second. We're back to this magnitude expression right here. So that's 104. Exciting life in graduate school over there. Let's see, 104 minus omega squared, 104 minus 400 squared plus 20 times 20, that quantity again squared, we take the square root of all that. And so this is going to be equal to Droid 48 being a HP calculator emulator. 104 is our numerator, divided by the square root of 104 minus 400 gives us what? 296. That's minus 296 squared plus 400 squared. We do the square root of all that, so this is equal to, all right, let's see, 296 enter 2yx. Don't really need to worry about the negative when I square it, right? 400 enter 2yx. Should be able to do that in my head. I add those two terms together. I take the square root of those two, I divide that, and I multiply by 104. When I said divide by, and then I inverse that. So this is equal to 0.209. That's the magnitude G of J20. All right, that's easy. That's nothing to worry about. But the phase angle makes things interesting. Angle of G of J20 is equal to, once again, we still have this expression right over here. The angle of the numerator is still 0, but now we're doing the inverse tangent minus the inverse tangent of, the numerator is 20 times 20, which is 400, divided by 104 minus 400 is equal to minus the inverse tangent of 400 over 104 minus 400, what did I say? That's negative 296. Now, you got a negative of a funny thing here, okay? And you cannot say, oh, I'll just pull this negative inside there and then change the sign, there'll be both positives. That doesn't work. I suppose you could put the negative inside, and that will actually mean that you have a negative 400 and negative 296. That would work. That'll put you in the fourth quadrant. But let's go ahead and work it out step by step. First off, where does 400 as an imaginary value and negative 296 as a real value put you? Well, if this is negative, let's just call that 300, because 296 is pretty close to 300, so there's our negative 296. That means 400 is going to be about up there. 1, 2, 3, 4, something like this. All right, so I'm a little over here. So when I evaluate the inverse tangent of 400 over negative 296 on my calculator, I go 400, enter, 296, negative divided by, and I do the inverse tangent of that, I get negative 53 degrees. This does not look like negative 53 degrees, but that looks like negative 53 degrees or so. Okay, so that's what your calculator is going to do to you if you blindly use these. So I recommend you don't, for obvious reasons. I don't want you to get the wrong. I would like you to get the right answer. I love having tests that have got all the right answers. So, what are we going to do? As I said, you could possibly take this negative and put it on the inside like that. And you'll have a negative 400 for your real, for your imaginary part, and negative 296. That will actually bring you down to here. But once again, if I go ahead, now suppose I did that, I go 400 negative, enter, 296 negative divided by, and I do the inverse tangent of that, I'll end up with 53.49 degrees. And so I end up over here, because your calculator defaults, usual calculators default to the first and fourth quadrant. I think I said fourth over here, I meant the third. First and fourth quadrant. And we're in the third is where we should end up. So my process for doing that, I always try to draw it out. And I really would like for you to draw it out. You will get it right more often than not if you do that. If you do it this way, what I take a look at is I say, okay, what's this angle? Let's call that alpha. Alpha is equal to the inverse tangent of, well, this side is going to be 400. This side is now 296, and I can do it as a positive because I'm getting this angle. So it's going to be 400 over 296, like that. Yep, I'm living with this. I'm just like, whoa, wait, did I screw something up? Okay, 400, enter, 296, divided by inverse tangent of 53.5 degrees, which is no surprise because it's alternate interior angles, right? We know this is negative 53, so this should be positive. This magnitude should be the same thing. So that's equal to 53.499 degrees. It's a lot more resolution than we need. And the phase angle that I'm looking for is actually this. It's actually the negative of that, for that matter. So what I'm saying is that the inverse tangent of 400 over minus 296, and recognize that here's a negative, and here I'm not doing the negative. Okay, I'm just trying to figure out what is this angle, is going to be equal to 180 degrees minus this alpha is equal to 180 degrees minus 53.499, 180, this is 126.5 degrees. And as the infomercial says, I'm sorry, so this is the angle from here to there is 126.5 degrees. Now we need to use our negative. Okay, which means we're going from here to there. So really then, the angle G of J omega, the infomercial answer was, but wait, there's more. But this is going to be equal to minus 126.5 degrees. Angle G of J 20, my mistake on that. All right, so that's the way to do phase angles for something actually beyond the natural frequency is actually what that's all about. It's beyond the phase angle of negative 90 degrees. By beyond, I mean larger in magnitude. So I hope that gives you some insight into how to do those problems. I really do. Let's do number 4. This is where I guess you fast forward on the tape or something, or the video. How am I doing on time? Not great. right, number 4 says G of S is equal to 150 over S squared plus 30S plus 200, like that. That's a 200. So, of course, the first step I would recommend is G of J omega is equal to 150 over J omega squared, because that's a negative omega squared, so we have 200 minus omega squared. There's the real part. That's going to be a real part when we square J omega, plus J times 30 omega, like that. That's G of J omega. Again, you utilize the J squared there to give you negative 1. That's where we stop utilizing the J. Magnitude G of J omega is going to be equal to 150 over 200 minus omega squared, the real part squared, plus the imaginary part squared being 30 omega squared. No J in there. Leave that out. 30 omega squared, and the square root of all that fun stuff. So this is going to be equal to, that's essentially where we could drop it at this point. That would be a sufficient answer to say what's the magnitude of this expression, G of J omega. Hang on just a second.